Praise the Lord, children. God has everything in His hands. So you need not worry or fear about anything. In whose, that is, the Lord and Savior Jesus Christ's hands, are the depths of the earth. The peaks of the mountains are His also. So we'll happily continue with Unit 11, Characteristics of Hydrocarbons. The first character is lower hydrocarbons are gases at room temperature. Example, methane, ethane are gases. They are colorless and odorless. The boiling point of hydrocarbons increases with an increase in the number of carbon atoms. They undergo combustion reaction with oxygen to form carbon dioxide and water. Alkanes are least reactive when compared to other classes of hydrocarbons. Alkynes are the most reactive due to the presence of the triple bond. Alkanes are saturated, whereas alkenes and alkynes are unsaturated. They are insoluble in water. Now you'll watch a video to test and to identify saturated and unsaturated compounds. In this video, you have to observe the addition of bromine water to alkanes and alkenes.
The tube on the left contains the saturated hydrocarbon cyclohexane. The tube on the right contains the unsaturated hydrocarbon cyclohexene. First, brown-red bromine is added drop by drop to the left-hand tube containing saturated hydrocarbon. As the bromine is added, it dissolves in the cyclohexane. The color remains when the solution is stirred because bromine does not react with saturated hydrocarbon. Now, liquid bromine is added to the unsaturated hydrocarbon cyclohexene. The red-brown color disappears as the bromine mixes with the cyclohexene. This is because the bromine reacts with cyclohexene, adding to the double bond. This reaction is a very convenient test for the presence of a double bond in a molecule.
Now, let's see the classification of organic compounds based on functional groups. The structural frameworks of organic compounds are made of carbon and hydrogen, which are relatively less reactive. But the presence of some other atoms or group of atoms makes the compounds more reactive and thus determines the chemical properties of the compound. These groups are called functional groups. A functional group is an atom or group of atoms in a molecule which gives its characteristic chemical properties. The chemical properties of an organic compound depend on its functional group, whereas its physical properties rely on remaining part of the structure. Carbon to carbon multiple bonds, C double bond C and C triple bond C, also are considered as functional groups as many of the properties are influenced by these bonds. Other functional groups include OH, CHO, COOH, etc. For example, ethane is a hydrocarbon having molecular formula C2H6. If one of its hydrogen is replaced by OH group, you will get an alcohol. Leaving the functional group, the rest of the structure is represented by R. Thus, an alcohol is represented by ROH. A series of compounds containing the same functional group is called a class of organic compounds. In this table, you can see the various classes of families of organic compounds and their functional groups. Alcohol, OH. Common formula ROH. R is the alkyl group. Example, ethanol, CH3CH2OH. Aldehyde, CHO. Common formula RCHO. So, aldehyde, example for aldehyde, CH3CHO. That is acetaldehyde. Ketone, C double bond O. R, COR. There will be two alkyl groups. Example is acetone, CH3, COCH3. Carboxylic acid, COOH, or COOH. Acetic acid, CH3COOH. That is the example. Ester, C double bond O and OR. R, that is the alkyl group, then COOR. Methyl acetate, CH3COOCH3. Ether, OR. ROR is the common formula. As you all know, R is the alkyl group. Dimethyl ether is the example, CH3OCH3. Homologous series. Homologous series is a group or a class of organic compounds having same general formula and similar chemical properties in which the successive members differ by a CH2 group. Let us consider members of alkanes as given in this table. Their condensed structural formulae are given below. Methane, CH4, ethane, CH3CH3, propane, CH3CH2CH3, butane, CH3CH2 twice CH3, pentane, CH3CH2 thrice CH3. If you observe the above series, you can notice that each successive member has one methylene group more than the precedent member of the series, and hence they are called homologs. Characteristics of homologous series. Each member of the series differs from the preceding or succeeding member by one methylene group, that is CH2 group, and hence by a molecular mass of 14 AMU, that is atomic mass unit. All members of a homologous series contain the same elements and functional group. They are represented by a general molecular formula, example alkanes, CnH2n plus 2. The members in each homologous series show a regular gradation in their physical properties with respect to their increase in molecular mass. Chemical properties of the members of a homologous series are similar. All the members can be prepared by a common method. Next we go on into nomenclature of organic compounds. Why do we need nomenclature? In ancient days, the names of organic compounds were related to the natural things from which they were obtained. For example, the formic acid was initially obtained by distillation of red ants. Latin name of the red ant is formica. So the name of the formic acid was derived from the Latin name of its source. Later, the organic compounds were synthesized from sources other than the natural sources. So scientists framed a systematic method for naming the organic compounds based on their structures. Hence, a set of rules was formulated by IUPAC, that is International Union of Pure and Applied Chemistry, for the nomenclature of chemical compounds. Components of an IUPAC name. The IUPAC name of any organic compound consists of three parts: root word, that is the parent, prefix, suffix. These parts are combined as per the following sequence to get the IUPAC name of the compound. Prefix plus root word plus suffix will give you the IUPAC name. Root word. It is the basic unit which describes the carbon skeleton. It gives the number of carbon atoms present in the parent chain of the compound and the pattern of their arrangement. Based on the number of carbon atoms present in the carbon skeleton, most of the names are derived from Greek numerals. This table shows the root words for the parent chain of hydrocarbons containing 1 to 10 carbon atoms. The 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, meth, eth, prop, but, pent, hex, hept, oct, non and dec. Okay. Then prefix. The prefix represents the substance or branch present in the parent chain. Atoms or group of atoms other than hydrogen attached to the carbon of the parent chain are called substituents. This table presents the major substituents of organic compounds and respective prefix used for them. The substituent, if it is F, then the prefix used is fluoro. Cl, chloro, Br, bromo, I, iodo, NH2, amino, CH3, methyl, CH2, CH3, ethyl. Suffix. The suffix forms the end of the name. It is divided into two parts such as primary suffix and secondary suffix. The primary suffix comes after the root word, that is the parent. It represents the nature in carbon-to-carbon bonding of the parent chain. If all the bonds between the carbon atoms of the parent chain are single, then suffix ane has to be used. Suffix ene and yne, ene and ine, are used for the compounds containing double and triple bonds respectively. The secondary suffix describes the functional group of the compound. Now you can see this in this table. Alcohol OH, the suffix will be OL. Aldehyde CHO AL. Ketone C double bond O ONE. Carboxylic acid COOH oic acid. IUPAC rules for naming organic compounds. Rule 1. Identify the longest chain of carbon atoms to get the parent name, that is the root word. Rule 2. Number the carbon atoms of the parent chain beginning at the closest end of the substituent or functional group. These are called locant numbers. If both functional group and substituent are present, then the priority will be given to the functional group. Rule 3. In case of alkenes and alkynes, locate the double bond or triple bond and use its locant number followed by a dash and a primary suffix. The carbon chain is numbered in such a way that the multiple bonds have the lowest possible locant number. Rule 4. If the compound contains functional group, locate it and use its locant number followed by a dash and a secondary suffix. Rule 5. When the primary and secondary suffixes are joined, the terminal E of the primary suffix is removed. Rule 6. Identify the substituent and use a number followed by a dash and a prefix to specify its location and identity. Now, based on these rules, let's substitute some examples. Let's see some examples. The first one will be pentane, CH3, CH2, 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 CH3. Step 1. It is a 5 carbon chain and hence the root word is pent according to rule 1. Step 2. All the bonds between carbon atoms are single bonds and thus the suffix is ane. So its name is pentane, pentane. Example 2. The compound is 2-methylpentane. You can see 5 carbon atoms. CH3, CH, CH2, CH2, CH3 and you can see the methyl group attached to the second carbon. Step 1. The longest chain contains 5 carbon atoms and hence the root word is pent. Step 2. There is a substituent. So, the carbon chain is numbered from the left end which is closest to the substituent, rule 2. Step 3. All are single bonds between the carbon atoms and the suffix is ane. Step 4. The substituent is a methyl group and it is located at second carbon atom. So, its locate number is 2. Thus, the prefix is 2-methyl according to rule 6. The name of the compound is 2-methyl plus pent plus ane. So, 2-methylpentane. The next example is 3-methylheptane. You can see 1, 2, 3, 4, 5, 6, 7 carbon atoms in the longest chain. So, step 1, the longest chain contains 7 carbon atoms and hence the root word is hept. There is a substituent. So, the carbon chain is numbered from the end which is closest to the substituent according to rule 2. Step 3, all are single bonds between the carbon atoms and thus the suffix is ane. Step 4, the substituent is a methyl group and it is located at third carbon. So, its locate number is 3. Thus, the prefix is 3-methyl, rule 6. Hence, the name of the compound is 3-methyl plus hept plus ane is equal to 3-methylheptane. This is the structure of 3-methylheptane. Now we move on into the next example, pent-1-ene. Step 1, it is a 5 carbon atoms chain and hence the root word is pent according to rule 1. Step 2, there is a carbon to carbon double bond. The suffix is ene, ene. Step 3, the carbon chain is numbered from the end such that double bond has the lowest locant number as shown below according to rule 3. Step 4, the locant number of the double bond is 1 and thus the suffix is 1-ene. So, the name of the compound is pent plus 1-ene is equal to pent-1-ene. IUPAC nomenclature of other classes solved examples. First example that we are going to see is propan 1-ol. Step 1. The parent chain consists of 3 carbon atoms. The root word is prop. Step 2. There are single bonds between the carbon atoms of the chain. So the primary suffix is ane. Step 3. Since the compound contains OH group, it is an alcohol. The carbon chain is numbered from the end which is closest to OH group. Step 4. The locant number of OH group is 1 and thus the secondary suffix is 1-ol. The name of the compound is prop plus ane plus 1-ol is equal to propan 1-ol. In the terminal E of the ane is removed as per rule 5. The next example is acetic acid. Step 1. The parent chain consists of 2 carbon atoms. The root word is eth. Step 2. All are single bonds between the carbon atoms of the chain. So the primary suffix is ane. Step 3. Since the compound contains the COOH group, it is a carboxylic acid. The secondary suffix is oic acid. The name of the compound is eth plus ane plus oic acid is equal to ethanoic acid. Now in this table, you can see the IUPAC names of homologues of various classes of organic compounds. First, let's see about alcohols. When the carbon atom number is 1, it is methanol. When the carbon atom is 2, it is ethanol, 3, propanol, 4, butanol and 5, pentanol. You can see the number of carbon atoms in each member. The second class is aldehydes. When the carbon atom is 1, it is methanal, 1 carbon atom. 2 carbon atoms, ethanal. 3 carbon atoms, propanal. 4 carbon atoms, butanal. And 5 carbon atoms, pentanal. The next class, ketones. You cannot find any member for carbon atom 1 and 2. For 3, propanone. 4, butanone. And 5, pentanone. The last one is carboxylic acid. When there is only 1 carbon atom, it is methanoic acid. 2 carbon atoms, ethanoic acid. 3 carbon atoms, propanoic acid. 4 carbon atoms, butanoic acid. And 5 carbon atoms, pentanoic acid. Hope you understood the IUPAC names clearly. Thank you.